Good afternoon, everyone, and welcome to the Optimizing Unreal Engine 4 for Fortnite Battle Royale Tech Talk. It's actually going to be split up into two parts. Part one is going to focus on game thread optimizations and what it took to get console to run at 60 FPS. Part two is going to focus on what it took to get the mobile build running, and also content and tech art optimizations that were necessary for everything that we're going to talk about here today. My name is Carlos Cuello, and I'm the lead engineer on Fortnite. And I've been really fortunate enough to see sort of the evolution of Fortnite over the last several years. One of the biggest changes and the biggest evolutionary changes was the introduction of Battle Royale last year. I think from initial branch creation to launch was about 10 to 12 weeks, which is crazy. 10 to 12 really long weeks, by the way. And it sort of just showed how such much of a great structural foundation Fortnite Save the World was. We could probably talk for hours about what that took and how much work it took to get that up and running, but today we're going to focus on optimizations and performance. It turns out that Save the World and Battle Royale are actually fairly different in terms of performance characteristics. Save the World is all about having 100+ AIs on screen at any one time with lots of particle effects going off in every direction. On the dedicated server, we have to worry about navigation mesh and AI behavior. We get significantly higher gameplay ability usage. It's just a very different game. Battle Royale, on the other hand, is probably one of the most technically challenging gameplay experiences we've ever built at Epic. It's got the largest map with the most players and the most platforms that we've ever supported. For the map, I believe our level is about 2.5 kilometers by 2.5 kilometers. And it's the first UE4 game that we've built, internally at the very least, that utilized level streaming. James Golding is going to talk about this next when he talks about game thread optimizations. For the players and getting 100 players in a match, we actually not only had to do some very low-level dedicated server optimizations, but we had to sort of fundamentally rethink how we do player replication in the engine. James is also going to talk about this next. And for the platforms, boy, these platforms, it's kind of crazy. It's kind of like Oprah, you know, where it's like you get a Fortnite, and you get a Fortnite, and everyone gets a Fortnite. But it sort of goes to show our sort of philosophy at Epic, where we want everyone to be able to play Fortnite on whatever device they have, with their friends especially. And one of the most important parts of that is making sure that we have the highest visual fidelity and performance on whatever platform you're playing on, whether it's a 10-year-old integrated graphics chipset, or an iPhone 6s, or hopefully lower in the future, or you're playing on a 1080 Ti, or just last week in the office, we're showing a video of a $20,000 gaming rig playing Fortnite. That's really important. Nick Penwarden is going to talk about this later today also. Another big part of sort of what we think is our critical success is our ability to make just gameplay impactful and just constantly improving the player experience build to build, week to week, including the technology in the Unreal Engine. In fact, almost everything that we're talking about here today was released after launch, and almost everything actually was probably in the last 6 to 8 weeks of this year. And that includes running on 60 FPS, level streaming, supporting mobile. It's really exciting to be able to do this. Another thing that we think is critically important, and finally, and we can get to the meat of the topic, the talk, is just our philosophy at Epic and that sort of symbiotic relationship between our games and our engine. And even though a lot of what you're going to see here today is very focused on optimizations that were necessary for Fortnite, all these things are going to make its way back to the engine, and we'll be able to allow developers in this room and across the world to be able to deliver some of these same experiences. So without further ado, I'm going to introduce James Golding, who's going to talk about game thread optimizations. Thank you.
Thank you, Carlos. So today, as Carlos says, I'm going to talk about how we tackle taking this game and the sort of game thread gameplay side of it, running on the CPU, and scaling it across all the different devices, the 60 hertz on console and onto mobile devices. So this is really the challenge with this game. It's 100 players, right? So there's a lot of challenges you gotta tackle to get this to work. And so this work involved people on the engine side and on the game side, a whole number of different people contributing to it. And because there's such a large number of players, there's a lot of variability in what's happening in the game. It could be everyone lands in one place, and so you get a lot of players suddenly in one area around you. So we need to scale not just with the hardware that we're running on, but also with what's going on in the game. So we have to be really quite nimble. So here are the topics I'm going to be talking about today. First, I'll introduce something called the Significance Manager, which is what we use to handle those very dynamic sort of combat situations. We'll talk about animation, which is obviously a big part of the work that we're doing with so many players. We'll talk about moving components around, in particular character movement. We'll talk about spawning things, systems that are ticking every frame. We'll also talk about level streaming, which is something we added a little bit later in the development of the game, but was a really important feature. And we'll also talk about server performance at the end, which is a slightly different aspect, but still really important. So first of all, I'm going to introduce the significance manager. The idea here is that we take the players that are in the level and we put them into significance buckets based on a couple of criteria: how far away they are, how large they are on screen, and whether or not we can see them. So players that are very close to you and that you can see will be in one of the higher priority buckets, and players that you can't see or are a long way away go into a lower priority bucket. And we basically set the maximum sizes of these buckets, so even if there's a ton of players near you, they won't all be processed at sort of high quality. We have a lot of knobs we can tune to reduce the quality, but still make it very playable. So this system then drives a lot of other scalability systems, so that's why we'll talk about it as we go through some of the other topics. This is actually based on an engine feature. It's been around for a little while in the engine, but there's a lot of game-specific logic that goes in there that you build on top of it. So other games can certainly build on this concept quite easily. So we talked about these different size buckets. We can make those different per platform. So on consoles, this is the current setup we have. We have 5 players in the highest quality bucket, and then we go 10, 10, and then the remaining 75 in the lowest quality. But on mobile, only 1 is actually in the highest quality. That's you, the player, that you can see. And then we start to drop off more aggressively because we just don't quite have the same CPU resources. So one of the most important things that we're using the significance manager to drive is animation. This is the way that we build characters in Fortnite Battle Royale. It's actually a modular character with 5 different meshes. So we have one base skeleton, which doesn't have any geometry on it. It's just the bones that we're animating with the animation logic, which we'll talk more about in a minute. But then there's 4 other meshes on top of this. There's a head mesh, a body mesh, what we call back bling, which could be a backpack or something similar to that, and the weapon that you're holding. All of these have separate animation graphs that they're running, which copies some of the information from the base skeleton, but can add other behaviors on top. That could be physics simulation or additional animations. This is a really cool system from a creative perspective because we can build all kinds of interesting cosmetics that people can have because they've got a lot of flexibility in adding new bones and simulation onto things. But it is a challenging one to make run really quickly because obviously if you've got 100 players with 5 meshes each, that's 500 meshes that you've got to process. So it's definitely challenging. So obviously, skeletal mesh LOD is a common topic in games, and that does help a bit on the rendering side, but it's less helpful on the game thread side. It does reduce the bone count, but that's being done usually on worker tasks, which we'll talk about in a sec, which doesn't help so much on the critical game thread path. So we did consider merging all these meshes together. We did this previously on Unreal Tournament 3 a few years ago, and that's what the screenshot is from. But we decided not to go down this path in Fortnite. One of the problems would have been it would have increased memory usage, because merging all those meshes together means every player has a unique mesh. And also, it reduces the flexibility. We really like this system where we can have different animation blueprints running on different parts of the character. So the first thing we need to do is check that we're doing the work in the most efficient way possible. The way the Unreal Engine animation system works is it breaks the work into 3 steps. There's an update phase where we gather information from the game state that we're going to use when animating the character. Then we do an evaluation step where we do the heavy lifting of animation decompression and blending. And we do a completion step where we take that state, we send it to the render thread for rendering, and we update any attachments and fire any notifies. That middle evaluation step can happen off the main thread on worker threads, which is much better on multi-core consoles and things like that. So we want to make sure that's happening. We did actually find a few bugs where it was incorrectly being done on the game thread, which we fixed in the engine, and will obviously be in upcoming releases. Now, blueprints are something which is very important to Unreal. We use it for all kinds of things, including the animation logic. Blueprints are great. They're really flexible. We use them all over the place in Fortnite. But they're not as fast as native code. And so you want to avoid using them if it's something that's going to execute every frame, particularly if it's complicated. And animation is one of those cases. So because Fortnite as a product had been in development for a while, there was quite a lot of iteration done over the years on the sort of core animation of the character, and a lot of that had been done in blueprints. So when we started this project and looked at the performance for each character, it was about sort of almost a millisecond to process. This is that first block you saw in the diagram where we're gathering all the state and sort of pre-processing it and setting it up for the animation. So one of the first things we did was a gameplay program. I had a look at that and turned it into sort of tidy C++ code, still trying to keep a lot of the flexibility and expose a lot of the parameters. But you can see we went from 0.93 down to about sort of 0.2 milliseconds. And you can see all those ticks on that top graph are all sort of blueprint function calls going off, which all go away once we converted most of that logic into C++. So this was a huge win and definitely a good step in the right direction. Another thing that we use in the engine is what we call a fast path for animation. The idea here is this is one of the animation graphs where the red nodes here are playing individual animations, and then into each animation we're doing some kind of logic to determine like a play rate. This could be some parameter from gameplay that we're offsetting and clamping and doing some pre-processing on before we use it. This logic was previously done in blueprints, but it means it's quite slow because you've got to run this blueprint logic in order to process that. We have a little lightning bolt symbol on nodes which are sort of on the fast path where no blueprint logic is being executed. But you can see in this, there's only one of those little lightning bolts on the first node. It's that little diagram there. So what we did for this project is on animation play nodes now, we have a few settings where we can scale, bias, and clamp the input to it and do it as part of the node rather than having to do it as separate blueprint logic. And after doing that, the initial graph turns into this, with lots of lightning bolts everywhere, which is what we like to see. And it means we're evaluating the whole graph, hitting that fast path, which again helps with that sort of middle evaluation section. But obviously, the fastest animation is the animation you don't do. So we want to try to avoid animating things when we can. One of the settings we use is this only tick pose when rendered option, which is a handy one to use, where when meshes are off screen, we don't need to animate them anymore. Pretty simple, really. We also found that we could avoid animating weapons that people were holding beyond a certain distance. You really don't notice it too much. And actually on mobile currently, we only animate the weapon that you're holding. We don't animate the weapon that other people are holding. So that's one less thing that we have to tick and update. We couldn't do this on things like backpacks and helmets, though, because those are copying the state from the underlying character. They're not just attachments. If you stop doing that, then they end up floating off the character. And actually, we did have this bug for a bit, and we fixed it recently. We have to keep ticking those things. Something else we added in this project is a concept of a static rendering path for skeletal meshes. For things like pickups, we want to be able to use the same mesh because we don't want to have two copies of the mesh in memory, but we don't need to do the whole extra work of animation or using a more expensive vertex shader to skin it. So we can now render a skeletal mesh as a static mesh, which is our sort of fastest path for rendering geometry, and that's what we use for all the pickups that you see in the world. So one of our other really useful tools in our battle against performance is what we call update rate optimization. The idea here is that rather than running the whole animation logic every frame, we run it at less than the frame rate of the game. So with no update rate optimization, we're evaluating everything every frame. That's what the far left-hand picture shows. But if we run the animation logic every 4 frames and interpolate between the results, it still looks pretty good. It's not fantastic, but it's, you can certainly turn that on for characters that are not right up in your face. If you push it too far, things can get a little bit weird looking, and you can see that at Euro 10, there's some sort of strange dance moves going on. We can also choose whether or not we actually interpolate between those results. We could just literally snap between the results, and only the one on the far right is using animation update every 4 frames and then no interpolation. This is a little bit faster because we don't have to do that interpolation work. We also don't have to update any attachments, but it looks a little bit janky. So we tend to only use this for really the lowest important significance and on platforms where we really need it. This, of course, is driven by significance. For some of the attachments on the character, we're using physics simulation. We started off using the anim dynamics node we've had for a couple of years. We switched most of those over, though, to use the rigid body anim node, which we talked about a bit last year at GDC, if you want to go back and look at that talk for a bit more detail. The nice thing about this is it's a single node, it's a faster solver, and it does give you more options. We've got like collision settings and things like that. So this is one of the my favorite cosmetics in the game. It's this sort of rubber shark on a pole, and that uses this rigid body node to do some simulation as you run around and wave it about. Another part of the whole animation process is calculating the bounding box for a mesh. And we couldn't just use a fixed bounding box for things because we've got all these really cool emotes that the animators have done, but it moves the character around quite a lot, so a fixed bounding box could probably give you some weird artifacts. So we do calculate the bounds for the character each frame using the collision shapes. But what we could do is for all of the attachments to the character, we just inherit the bounds from the parent. So we only have to calculate 1 bounding box, not 5 for every character. Another aspect of animation was what we call animation notifies. These are little events that we attach to the animation and play and fire logic as the animation plays. These are for use for things like footstep notifies, for sounds and particles, or in this case, for the trails behind the axe as you swing it around. These were originally implemented in blueprints, which is great, it's very flexible, but when we have so many players and we're really worried about performance, we wanted to convert those into C++ instead. That's pretty easy to do, but now you have to go through all your animations and switch them over to use the new version. And we use what we call an anim modifier, which is an editor script to run through all those. And I'll talk about those a little bit later, because it was a pattern that we used quite a lot in this project. We also used our async trace API, which means we're doing collision traces on a worker thread a frame late rather than right away for determining what the floor material is. And again, we can use the significance manager to skip that altogether for very distant players. So now we've got some characters animating. We need to start moving them around. The first thing we do here is just look at what's going on. We used event-based profiling quite a lot. You saw that a little bit earlier in that sort of timeline view, where we can see all of the things going on each frame. It's a very useful way to look at things. And there are a bunch of tools that do this. So we have a look at what's going on each time you move a component. We can look at all the things that are attached to it that also have to get moved. And we remove what we can. We found things like the weapons had a number of attachments that either weren't being used anymore or weren't relevant to the game type, which we could remove. I think we got our weapons from about 9 components down to 3, which is obviously an advantage. We also use this option called Auto Manage Attachment. The idea here is that you don't need to move around a component if it's not actually doing anything. If it's a particle system that's not playing, there's no point in me doing the logic of moving it. It's not particularly expensive to move, but with so many players in the game, you really want to save whatever you can. So we had this option available on particle systems, and then we added it to audio components as well. So if you've got an audio component that's not playing, it doesn't get moved until it starts playing something. And that'll be in 4.19. One of the slowest parts when you move components around is if that component needs to generate what we call overlap events when it touches something else. This is on by default, so you do want to look at those profiles and see if there's anything generating events you don't need. We really like our spinning tomato head in the game, but it doesn't really need to generate overlap events every time it moves, so we turned that off, and that saved a bunch of time. There's a bunch of other things like doors that open and a supply drop, which is generating more events than it really needs to, so we go in and trim those out. Another optimization we made to overlap events was to the way that we actually traverse all the components inside an actor to figure out whether we want to generate an event at all. In this diagram, this is the sort of attachment hierarchy of all the components inside an actor, if you can imagine that. And the red ones are the ones that want overlap events. Previously, we'd have to walk to every single one and say, do you want an overlap event? Do you want one? And so forth. What we do now is remember how many children I have that want overlaps, and if that number is 0, we just don't need to bother looking at them at all. And not touching the memory is better than touching it and doing no work at all. So this is an optimization that will go into the, I believe this is in the 4.19 release. So I mentioned earlier on that when it came to modifying large amounts of content, we started using editor scripts to do it. We actually use blueprints to do this, but we now have experimental Python support in the engine, and a lot of the same, anything we expose to blueprints on the editor side is also exposed to Python. So you could write Python scripts now, theoretically, to do this kind of work. So the way it works now is you can create a special kind of blueprint called a scripted action in the editor, and what make you now select some assets, right-click, and run that blueprint on those assets at editor time. You can even enter some input properties, and then it runs the logic. So here's the one that we use to replace notifies. It's pretty simple. You pass in the assets to it. It gets the set of assets that you passed. And then for each one of those, if it's an animation sequence, we call this replace anim notifies utility. And we're going to be spending more and more time exposing editor functionality to this system because we just found it really useful for auditing content and making bulk modifications to content. In the second part of this talk, the second hour of this talk, the artist will talk a little bit about some of the other things they did with this. OK, so now we're moving some components around, we're animating them, we found some good savings there. We'll talk about character movement specifically. So the default for character movement is what we call full client predictions. This is where we run the full client movement code, the full character movement code on the client for every player that you see. The way our character movement code works is it basically sweeps a capsule through the world, and if it hits something, it stops, which works very well, but it is quite expensive. And so the idea was we wanted a lower quality, a cheaper way of doing that character movement, so we didn't have to always do full character movement for all of the clients that you could see. So we use interpolation instead in those cases. When the server tells you where another player is, we simply interpolate the mesh to that position rather than running the full client prediction code. In future, we're probably going to add some more fine-grained control so we can sort of turn on and off individual elements of it, for example, checking what the gradient of the floor is for foot IK and stuff like that. We can also throttle the ground checks to do them at a lower frame rate. So here's comparing those two ideas. The top one is the higher quality but more expensive full prediction. So here we're taking from the server what the inputs were and we're replaying that movement so it's doing exactly what would happen. So for example, if there was a step, you'd actually see the player move up over it. And this is the highest quality. On the bottom, you can kind of see that capsule is sort of teleporting around. That's as it gets an update from the server each time, and we're just interpolating the skeletal mesh between those positions. So it doesn't look terrible, but it's not as snappy as doing the full client prediction. So again, this is driven by significance, and on mobile, we can use the lower one for a lot more of the players. OK, so we've got some characters running around. They're animating. We've got other things like projectiles and everything else moving around in the world. We now looked at spawning objects. That's creating something, bringing something into existence. And there's a lot of this that goes on in the world. If you've seen high-level Fortnite players online playing Battle Royale, they make a lot of walls really quickly. They also are opening chests, players are being eliminated and spawning loot, things are coming in and out of network relevancy, projectiles are being fired. There's just a lot going on in this game. So once again, we turn to our trusty profiles, and we look to see what work is being done when we create those things. One of the things that you can do to help improve how quick you can spawn something is reduce its component count. And it's also useful to bear in mind that C++ components are faster to spawn than Blueprint components. So sometimes it's worth converting components into a native base class. Another pattern that we saw was sometimes we would register it. So that means where you actually get the component ready to play and then start modifying properties about it. And it's better to do the setup and then the registration. Another thing we found while we were looking at this was that, in particular, copying parameters between material instances was actually a very slow process. It was actually really only supposed to be done in the editor, but was used at game time to sort of configure some of the pickups and stuff. So we added a fast path for that and made sure that was being used. Once again, as always, these are engine optimizations which are going back into the engine for everybody to use. One thing in particular that we did was add the concept of particle pooling. One of the most common things that we spawn in the game, particularly a game with lots of combat, is particle effects, whether it's hit markers on someone or particle effects from aspects, things being spawned, that kind of stuff, or explosions. So by pooling them, we basically keep these sets of components around that we can use again and again without having to pay the allocation cost and the setup cost for those things. So now our sort of engine spawn emitter function has a pooling method that you pass in to specify how you want to control these things in their lifetime. OK, so we're spawning some stuff. We're running some things around. We're going to look at some of the other systems that are being ticked and doing work every frame. The HUD was one of the things that we looked at that does work every frame. It was taking about 2.5 milliseconds, which isn't too bad if you've got a 30 hertz game. But if you're running at 60 hertz, or if you're trying on mobile, where this number would get even larger, it was something we wanted to look at. So that we did make some optimizations here. We removed some of the Blueprint logic. Once again, Blueprints are great and really flexible, but not necessarily the right tool if you're trying to do work every frame. I'm very much worried about performance. We also added what we call invalidation panels, which is a widget which will cache the results and only update it at a lower frame rate than every frame. And we could look at some other widgets that were slow and optimize those. So we saved about a millisecond through these, but we certainly aren't done yet. There's a lot more things we want to do with Slate over time. One useful console command when you're profiling a game is dump ticks enabled. This will list out all of the tick functions that are currently scheduled every frame. And so this is kind of makes for fun reading, as you can imagine. But you can often spot things that maybe shouldn't be happening every frame on the platform you're on. So we found lots of weather vanes that were gently moving in the breeze and cool creaking windmills and stuff. And we went through, and for some of these things, we made them based on significance or based on the platform. We might not do them. Or we might look at how the logic has been implemented and find maybe a faster way to do it. We try and work closely with our level designers. A lot of this adds personality. We don't just want to go through and just cut everything if there's a possibly way that we can do it and keep that personality. Another system that runs every frame is our time of day system. It's one of the cool things about Fortnite is that the time of day will change slowly as the game goes on. This is implemented in Unreal using a material parameter collection. And where we're setting parameters on this every frame. The way it used to work before is every time you change one parameter, it would send that command to the render thread. But we optimized it to only send one command, regardless of how many parameters you changed. Audio is another big part of the game, and obviously has to do some work. Most of this is done off the game thread anyway, but some of the work was still done there. We still have to process what we call sound cues, which are our sort of sound graphs where we can apply effects and things. Previously, we would evaluate those even if the eventual sound might not be played. So we added a prioritization system that we could run first to color loss them. We went from over 200 sound instances being processed each frame to about 50, which was a big saving. We also limit the number of audio sources on different platforms. On PC, it's about 32, and on Android and iOS, it's around 12 to 16. And we can turn off features on the platform as well, so things like reverb and EQ can be platform-specific. Texture streaming is another system that does a bit of work. Again, most of this was already off the game thread, but some work was still there, and we wanted to save where we could. So one thing we do on mobile is we can reduce quite how responsive the texture streaming is from, I don't remember the exact numbers, but it's not quite as responsive in the game. It doesn't have to do quite as much work every frame. But we do keep it responsive in the front end so that when you're swapping between your cool cosmetics in the shop, the textures come in nice and quickly. So now I'm going to talk a little bit about level streaming, which is a feature we added in 2.2.0 version of Fortnite in January of the year. This was a big change. So previously, we'd load the whole map up front, and we changed that to only loading the parts of the map that are around you dynamically as you dived off the battle bus or as you ran around the map. So as you can imagine, this is a pretty big change to drop into a game that was already up and running. So why did we do it? Well, we wanted to reduce the overall memory usage, and we also wanted to add more variety to the map. Our level designers have so many cool ideas and of areas they wanted to add, but there was no way to do it and load all of that variety at once. So we needed to only load the assets for the area that you're in. It's also optimizes our rendering and our gameplay systems. There's just less stuff in the world that we have to process, which does help. So there's 3 parts to level streaming. We have to load the data in the first place. Then we have to do what we call registering the components, which gets them ready to take part in the engine. This is generally creating collision state and rendering state. And then we have to actually get the gameplay systems up and running for anything that might have been loaded. When we're loading data, that again is broken down into 3 subparts. First, we have to get it off the hard drive. There's an I/O section. Then there's a deserialization step, where we have to turn that data, get that data into memory. And then we have what we call post-load, which is various operations that need to be done to bring that data into existence, any kind of initialization steps. The I/O was already done on a worker thread. The deserialization was moved onto what we call the async loading thread. That's a newer feature in the engine, which gets it off that critical path. And the post-load is generally not something that you can do off the game thread. We time slice that in using an adaptive time step. So when you're skydiving, when we're really worried about streaming performance, we use 5 milliseconds each frame to do that post-load work. And when you're on the ground running around, we don't need to give it quite as much because you're not moving as fast. So we give it about 3 milliseconds. Another thing we tried to do is overlap level loads. Rather than finishing one level before starting the next one, we could start the I/O for the next one while we're doing the post-load for the previous one. So by doing that overlap, we sort of keep the I/O really busy. We also found that material instances were particularly slow to load due to the way that they processed some data. We made some optimizations here to make them a fair bit faster. There's still a bit more work to do. OK, so we've loaded all this stuff. Now we need to register these components. Again, we use an adaptive time step similar to the post-load. When you're skydiving, it's about 5 milliseconds a frame. And when you're on the ground, it's about 1 millisecond. And we also added the option that if for some reason we are render thread bound or GPU bound, we can use that spare game thread time to get those components registered more quickly as well. We just sort of fill in the gaps there. Note that these time steps are for running at 60 hertz. If you're running at 30 hertz, either if that's your option on console or on mobile, they'll be double the times that I stated. So we did look into reducing the component counts by merging instances of static meshes, which were never going to be destroyed together, using instant static mesh component. We didn't end up using this because we also have to be concerned about vertex count. But the tool was actually pretty useful. We added it as an extension of our existing merge actors tool. So this will be available in the 420, because we do think there are cases where this would be useful. So then we're going to look at begin play. This is when we bring the gameplay logic up. One of the examples was these cool ladybirds that flap around the level and make you think that you're being sniped from behind a bush. Unfortunately, they had a long warm-up time, which can so there's a sudden block of work that got done when they got brought into the game. That was quickly fixed by a quiet word in the artist's ear. Another aspect, which was a bit more interesting, is the building system. And the way that works is it has to know all the neighbors. As you know, when you knock down something at the bottom, the whole building has to be destroyed. So there's this connectivity graph that has to exist. That was previously calculated when the level was loaded, but that's quite expensive. It has to do these collision tests to find its neighbors. So we changed it to be done at save rather than at load, and that was a big help. So the final thing I'm going to talk about today is server performance. Obviously, 100 players in a game is a big challenge. We have 50,000 replicated actors. We have 100 connections going on. There are 400 streaming levels. We have to make sure we synchronize between the server and the client so it knows what's going on. And we want to try and maintain a solid 20 hertz tick rate on the server. So we can start with some sort of easier things, like making sure the network update rates are set correctly. We can make sure the relevancy distances are right, so we're only replicating things that are close to you. And we can use the dormancy system that we added a few years ago, which basically shuts down the network connection for some objects when they're static. Obviously, a lot of the world is not static at not changing at any one time. But that only gets you so far. So for the last couple of months, we've been working on something called the replication graph. This is a total rewrite of the way that we process network relevancy. Rather than each actor determining for each connection whether it should send data and what data it should send, it centralizes this whole process. So we're not using these isNet relevant for or getNet priority functions. So the way this works is you start with your list of potentially replicated objects, and you run it through a graph of sort of filter nodes. Each node generates lists in advance that you can then use when you're sending data to each connection. So this could be a spatial grid, where we're building a set of actors for each part of the world. It could be a set for your squad. It could be a set just for you. So we pre-build all these lists, and then for each connection, it can very quickly assemble the set of information it needs to send to that client. So this will be coming online quite soon. This is something we're testing at the moment, and we'll have to see when we can release it. But we think this will be a really big improvement for server CPU usage. This is a diagram of what we think the replication graph for the server will look like, with a bunch of different cells doing different sorts of processing and prioritization. Another optimization we've already made is that previously each actor, when it was sent to a client, would serialize the state into a blob of data which would be sent. And now we do sharing there. So we only serialize it once and can send the same blob to multiple clients. You can't do this with all the data. Things like object references, and depending on whether you own the object or not, make this a little bit more complicated. But it still saves some of the work. One thing to think about with server performance is a lot of the time optimizations you've made for the client will still help. So reducing component count, you're still spawning the actor on the client and the server, so that'll help that performance. Another thing we need to make sure is working correctly is what we call combining moves. If your client is running at 120 hertz, it could be sending an update to the server, what we call an RPC to the server, every one of those frames, which is a lot of information for the server to handle, because the server has to handle incoming data as well as sending out outgoing data. So the less that the server is having to deal with, the faster it'll run. So we merge moves together when we can. This picture shows what I mean. On the left, we're just running in a straight line. So in this case, we can merge those into one packet that gets sent at some minimum update rate. On the right, though, where we've been moving and then turn quickly, we can't combine those together. We want to send that straight away. We never want combining to add latency to the proceedings. We know that people need to get that information as quickly as they can to the server to have a responsive game. But it does mean we can dramatically reduce the amount of data that we're sending and the work that the server's doing. And it reduces bandwidth as well. We recently fixed the bug where jumping was not combining moves properly. So now we're using slightly less bandwidth. And the final thing on the server that we looked at was animation. We don't need to run the animation logic on the server. It's not going to be perfectly synchronized anyway. And we use different methods to verify things like hits on the server. So we can turn off animation altogether, and we can also disable the collision shapes. This is actually the collision we use for a player on Fortnite. You can see it's a number of collision shapes going on there. But we don't need to move those around on the server, so that skips a whole bunch of work that we might be doing otherwise. And we also get rid of any of the cosmetic components like particles and audio. So that's a ton of different aspects. As you can see, we've covered a lot of ground there. And what I'm now going to do is hand off to Nick Penwarden, who's going to talk about taking the console-specific parts of this and getting the game to run really well on consoles. So thank you very much.
Thank you, James. Thanks, everybody, and good afternoon. Thanks for coming out to our tech talks and learning how we optimized Fortnite Battle Royale. So I'm going to talk about getting Fortnite Battle Royale to run at 60 frames per second on consoles. Just a bit of motivation, why 60 frames per second? Fortnite Battle Royale is a PvP game, so low input latency and smooth frame rate are very important. And so we decided we wanted to bring that to Battle Royale on console. Making a 30 FPS game run at 60 comes with some challenges. We originally built all of the content and really the game itself with 30 frames per second in mind. So how do we get it down to 60 frames per second? On the GPU side, we mostly worked with scalability and dynamic resolution. And on the CPU side, we had to do a lot of optimization, which is what James was just talking about. We actually went with an in-game option for 60 FPS, which is maybe a little unusual. We wanted to give people the option to pick between visual fidelity or preferring frame rate. This added a bit of extra headache in terms of additional QA, additional testing, and so on. And ultimately, we'll see whether we keep the two options. But right now, it's kind of nice to have both. So the way we did this is we leveraged device profiles in UE4. So device profiles allow you to specify different scalability options based on the platform. So in this case, what we did is we just made up a device profile for 60 frames per second mode. In this case, the base Xbox. And we just tweaked a couple of settings where we had to deviate from the base Xbox settings. So for instance, we pulled in view distance a little bit, disabled distance field ambient occlusion, scaled back shadow quality a little bit, stuff like that. So just to show you a couple of results, this is an image from the game running at 30 frames per second on a base Xbox One. And this is the same area with the visual trade-offs that we had to make to get it running at 60 frames per second. So if I go back and forth, you can kind of see the nice soft shadow under the truck goes away. That's distance field ambient occlusion. But mostly the scene stays pretty faithful to the visual target that we had for the game. Talk a little bit about profiling. The way we approached this problem, we had our QA team gather profiling data during our daily 100-player playtest. This was really important because in order to get to get data from a battle royale game, you need a lot of people. So it's not something you can sit at your desk and profile very easily. That we would have them grab actual profiles. So once we would look at the data and see the number of hitches went up or frame rate has gone down, we could dig in and see where is that time going and where do we need to work on optimization. Here's an example result out of one of those play sessions. This is just a graph of frame time throughout the course of the match, including also GPU time and the game thread time and the render thread time. We also gathered analytics data, both from the wild, but also internally. We keep metrics like how many hitches we see per minute, how long the hitches are. Missed vsync percentage is basically how many frames did we drop during the course of the match. And then some information about the different thread times. We also send back some information on what resolution the game is rendering at. This is important when you're using dynamic resolution to scale the game because regressions in GPU performance can turn into visual quality regressions rather than frame rate regressions. And we want to track that and have metrics for what our target resolution is. And we had a couple, for instance, like we tried to make sure we never dropped more than 2% of frames during the course of a match and fewer than 5 hitches per minute. We defined a hitch as a 60 millisecond frame or higher. Talk a little bit about GPU optimization. Fortnite is heavily dependent on dynamic lighting. You can destroy just about any object in the world. You can also build new structures. We have continuous time of day. That means we can pre-compute almost nothing. It's also open world in the sense that we have very long draw distances. You can see the large points of interest and trees and so on from pretty much the other side of the map. Also means we have a large number of unique objects and materials. So I'm going to talk a little bit about dynamic resolution and temporal upsampling, since this was one of the key features that allowed us to ship the GPU at frame rate without reducing visual quality too much. So this video here is recorded on an Xbox One base. And we can see as we're running around, when we were inside, we were running at full resolution. The graph on the bottom is showing resolution. Right now we're between 70 and 100, probably around, looks like 87%. And on the top you can see the GPU frame time. So you can sort of see as GPU frame time goes up, we drop resolution to compensate. And so there we saw it went up, started to spike, so we dropped resolution to keep it below, or to keep the game running at less than 16.7 milliseconds per frame. And then as we're running around and GPU time drops, we bump up resolution a bit and restore quality. The other thing to notice is if you look closely at this video, I think you'll find it very difficult to tell when we're changing resolution. It doesn't stick out, and that's because of the temporal upsampling technique that we're using. So talk a little bit first about temporal upsampling. It's an extension of the temporal anti-aliasing that we've had in the engine for a while. Brian Karras presented this at SIGGRAPH in 2014. It allows us to upsample based on previous frame history. Ubisoft and Activision have also presented similar techniques over the course of the last year that you may want to look into for deeper technical details. And again, the reason that we use it in this context is we wanted to hide the resolution changes that you would otherwise see with spatial upscaling. So if you take a look at the image, basically the idea is we render out the scene, we do some number of post-processing like depth of field, we do the temporal upsample to our output resolution. There are some post-processes that have to happen after that point, motion blur, bloom, and the tone mapper in this case, and then we render the UI and present. One side note about this, when you're doing temporal upsampling like this, you have to MIP bias all of your textures. This is necessary because since we're actually accumulating results and displaying at the final output resolution, if we were just to sample textures without any sort of MIP bias, all of the textures would look blurry. So I don't know how well it shows on the screen up here, but without a bias, the textures end up looking quite blurry. With a little bit of a bias, we can bring back some of that quality. If we found that we had to tweak it a little bit, so there's a little bit of a fudge factor in there. we were seeing just a little bit too much aliasing and noise if we were using the exact same MIP calculation we should be using for the target resolution. So with temporal upsampling in place, the idea is that we basically take a constrained viewport and we scale it. We render it up into the upper right-hand corner, and then we use temporal upsample. We use this as the input to temporal upsampling to generate the final image. And because this hides the resolution changes well, we update the resolution we render at every 8 frames. So with dynamic resolution, we get to set a budget. So we specify exactly what frame time we want to see on the GPU, as well as how much headroom we want to allow. And then we set the ranges for screen percentage. Originally, we wanted to vary between 50% and 100%, but we found that 50% of 1080p was just too blurry. Temporal upsampling couldn't reproduce a good enough image, so we ended up capping it at 65% on the low end. On Xbox One X, we did go between 50 and 100% because our target output resolution was 1800p, and rendering at 900p ended up looking okay with temporal upsampling. We also added an optional spatial upscale at the end. This is because some of the post-processing does happen after the temporal upsample, and we might not be able to afford those passes at native resolution. We primarily use this for Xbox One X, where we want to render the UI at full 4K, but didn't want to render the motion blur, bloom, and tone mapping at 4K. So we rendered those at 1800p, upscale to 4K, and render the UI at native resolution. Here was our final dynamic resolution configuration for each platform that we shipped on. So the output resolution was sort of our 100% target, 900p on Xbox One, 1800p on Xbox One X, and 1080p on both PS4 and PS4 Pro. And as I mentioned, the different ranges that we allowed dynamic resolution to scale between. One other interesting point with dynamic resolution, it's really important to have an accurate GPU frame time. And this means you need to take into account idle time on the GPU. We can do this on consoles, but on PC, this gets really tricky. To tell whether or not another process has added some GPU work into the picture, or whether there's idle time because you're actually CPU bound. Because of that, we don't currently support dynamic resolution on D3D11, but it's something we're working with the hardware vendors on to see if we can get the accurate data that we need. So finally, this is the result that we were able to see. This is from a PlayStation 4 session. So here at the top is an entire Battle Royale session. The top graph is the resolution that we were rendering at. In this case, 100, meaning 100% of output resolution, or 1080. And the bottom graph is GPU time. So we're really pleased with this result. Basically, looking at the GPU time, you can see that we're always somewhere in the neighborhood of 15.5 to 16.5 milliseconds of GPU time, and it's quite steady. We rarely bump up over our budget of 16.7 milliseconds, and you can see a number of times where we scale down resolution. The big dip in the beginning is when the player is skydiving. We're doing a lot of streaming. The player can see the entire map, so there's a pretty heavy load on the GPU at that point. Moving on to other GPU optimizations, we do a full Z prepass on Fortnite. Couple benefits from this. This allowed us to only evaluate the opacity for mass materials in the prepass and then use depth equal in the base pass. Saved us a bit of time. It also enabled us to use the async compute SSAO. Basically, after we do the prepass, we kick off an async compute job to compute SSAO, and while we're populating the G buffer, which can vary between being vertex bound and bandwidth bound, SSAO can use the free compute power to do its job. Dynamic shadows. So these actually have quite a high overhead on both the CPU and the GPU. For 60 frames per second mode, we ended up removing a shadow cascade, meaning we only had one shadow cascade on base consoles. we filled in the blanks with ray trace distance field shadows. This is a technique that Daniel Wright presented at SIGGRAPH back in 2015. Provides high quality shadows in the distance. There's almost no CPU cost. But it's still somewhat expensive on the GPU, about 2.5 milliseconds, which is really good for what we get, but when you're targeting 60 frames per second, that's a lot of GPU time. Just to show you what this ended up looking like in practice, on an Xbox One, the white line shows where our shadow cascade drops off, and we transition to distance field shadows. So if we didn't have this technique, this is what the game would look like, which would be rather poor. And this allows us to continue shadowing the rest of the world all the way out to the horizon. So the typical cost was around 2-3 milliseconds on an Xbox One, but could rise to as much as 8 milliseconds in certain cases, where, especially where you're seeing the entire map, and we have to consider a ton of objects for each section of the screen. So we have two parts, culling and ray tracing. And we made a couple of optimizations there to bring the cost down. So on the culling side, things like added an early view distance culling, as well as replacing the sphere test with a box test to get a tighter bound. So we end up doing less cone tracing. For the actual ray tracing parts, we packed the object data a little tighter and had a couple of optimizations like skipping the local sign distance field borders. As well as tuning the compute shader group size. The work ends up being very divergent, so using a smaller group size ended up being more efficient for us. We've also added a new lower quality ray trace distance field shadow mode, where we disable subsurface scattering and we lower the march count a little bit. The results of this is that with the optimizations, the standard quality version is now about twice as fast as it was, and the low-quality version is nearly 3 times faster than it was. So this got us from that 2 to 3 milliseconds down to around 1 millisecond on Xbox One base and allowed us to ship it. Let's see. So when we get to visual trade-offs, as I mentioned before, we ended up having to disable distance field ambient occlusion, since it costs up to around 3 milliseconds on the base Xbox. Because of this, we did have to, so I'll just use images to try to illustrate what I'm going to talk about. So in a building interior like this, distance field ambient occlusion does a good job shadowing the skybox and reducing the intensity of the skylight indoors. Without it, the interiors just look basically fully lit, or even close to unlit, really. So what we ended up doing is we just found a balance between reducing skylight brightness so it still looked okay indoors and okay outdoors, and increased SSAO a little bit, as well as increasing the kernel size of that a little bit, just to try to give the scene something. It's something that we're working on right now to try to see if we can come up with an optimized version. We think we might be able to get it down to around 1 millisecond with a couple of visual trade-offs, which would make it viable on at 60 frames per second, even on the base Xbox One. So it's a visual quality. It's a trade-off we'd rather not make, and so we're going to try to optimize it further to improve the look of the game. Vertex optimization ended up being where a lot of our work went, especially on the content front. It's because with dynamic resolution, we were able to scale pixel work very easily and automatically. However, it doesn't help at all when you're vertex bound. So stuff like grass can be particularly expensive. We had scenes where it was costing us up to 8 milliseconds on the Xbox One. So all of the sort of standard content optimizations, adding LODs, reducing vertex shader instruction counts for the wind animation, as well as we tuned the density and distance at which we cull a little bit in order to get those costs down. Moving on to CPU optimizations, the game thread costs can be very unpredictable compared to rendering work. But again, James already talked about that, so let's talk a little bit more about the rendering side. The two main costs, we have scene traversal, basically culling all of the objects into the scene down to what's actually visible, and then going through and actually drawing it all. And then there were a couple of resource update related costs in the engine that we had to address. So hierarchical LOD was a big win for us. Since you can see points of interest from the other side of the map, it was important to cut down the draw calls as well as to reduce the number of vertices you see in the distance. So we use the hierarchical LOD tools built into UE4, as well as the Simplygon proxy mesh tools to take a group of meshes like this and generate a single mesh that can be rendered in one draw call. Our parallel rendering work is often bottlenecked on init views, so this is basically the work to figure out what we're going to draw, all of frustum culling and occlusion culling, and then figuring out which passes each mesh renders in, and so on. We have to finish that before we start doing the massively parallel passes to go and actually issue all of the draw calls. So a couple tweaks to this to make sure that we're kicking off the parallel passes as soon as possible. So we do just enough work to figure out what meshes are going to render in the prepass, and then we kick that off so all of the worker threads can start chewing through the prepass, and then we continue and do further work to figure out what needs to render during shadow passes and so on. And level streaming was another change that made a big improvement here. Meshes that aren't loaded, we don't even have to consider, so that helps reduce the sort of scene traversal cost. We also, so the renderer has caches for pipeline state objects and bound shader states, and because the rendering is very heavily parallelized, we were finding a lot of lock contention on those caches. So some simple changes to use a read-write lock instead to allow concurrent readers. Since writes are fairly infrequent, this ended up being a pretty big win for us. Resource updates. So occasionally when we update resources, there are certain paths, for instance, creating a shader resource view or updating vertex buffers where the previous code, we'd have to actually go and flush all of the parallel work that we had previously kicked off and then update the resource and let parallel work continue. So rather than that, we made sure that we had update paths that could be done in parallel in these cases. This was particularly true for DirectX 12 on Xbox One. The implementation of how these are handled is platform specific, and we had already handled it on PlayStation, needed to add it for Xbox. On the PlayStation side, there were a couple of improvements, just the way we handle buffers internally in the tracking, particularly buffers that are needed for only a single frame. There was just a lot of complexity to make sure that those things lived as long as they needed to without being overwritten. And so we cleaned up a lot of that code. It's both simpler now and faster. On the texture streaming side, there were a couple of inefficiencies that we found. The biggest one is just that with a massive world like this, with so many objects, the total cost to go through every single object that we had loaded, even with level streaming, was very high. It happened on a different thread, but it could take a long time, and that could delay when we could stream in textures. So instead, we made a couple of optimizations where we can make decisions based on an entire level at a time for a texture. And then if we don't think that's going to actually cause us to make a different decision than a decision that we've already made, we just keep moving on. We don't have to look at every individual instance in that level. We also use profile-guided optimization. So in this case, we use replay data for it. So this allows us to, we capture a replay from a playtest, and then our build farm will be able to build the profile executable, and then take that along with the replay data that we've captured from a playtest, do an automated PGO run, generate the profiling data, and we incorporate that into the final built executable. So that's kind of nice. Since we're able to use replay data for it, we don't have to actually go and have QA play the game or something, or someone's got to run through and try to do a representative playtest just to get us the data we need. And that ended up being a pretty significant win for us. Between 1 and 2 milliseconds. So this is showing some replay data on PlayStation 4. The lower graph is obviously with profile-guided optimization. And finally, I think James talked about this already a little bit, but slate ticking was another bottleneck for us on trying to get to 60, where we were about at 2.5 milliseconds, and we were able to shave a millisecond off of that with just some good optimization, particularly using invalidation panels intelligently. So that's it. Questions? Oh, I hear we have no time for questions. So I guess those of us who gave the talk will be available in the lobby, I think, for questions afterward. Thank you so much for attending.